Okay, so anyway, let's continue. Any questions here, guys? Everything's all right? Okay, so we continue discussing the formal field series, CFT continuation. And so the first thing I promised that I will look back at the signs, and I did, and there are no mistakes. So we'll continue with my with my sign conventions. Everything will work out nicely. So what we did, we derived the following word identity last time. So we have a symmetry, then the variation of some operator A takes this form, minus epsilon over 2 pi I. I'm just copying what we had last time, and d2 sigma square root of minus G. The symmetry current A of sigma naught equals to 0. So the only constraint here is that sigma naught must be inside R, right? So remember what we did. We inserted an operator in our path integral, and we made a symmetry transformation with a compact support. It was non-zero inside some region R, and so it's important that this point where we're inserting an operator is inside that region as well. Okay, so I can write this down in the following form. So I'm just I want to write down instead of an integral as a relation without it, right? So how we can do this? Well, I can move it on the other side, right? We will find the following relations: d2 sigma, okay, of G sigma naught should be equal to. So this guy, I can put I on top here and put a plus sign here. So then this will be 2 pi over I epsilon delta A of sigma naught. And so I can write this down. I'm going to write it down as a relation without an integral. So we're finding that nabla A acting on JA, A of sigma naught equals to 2 pi over I epsilon 1 minus root G. And then I have a delta function, sigma minus sigma naught, and delta A of sigma. Okay? So we have this very nicely. So another thing that I want to do is to write down this integral around the boundary of our support domain. Well, so notice that all those guys depend on sigma, right? And so this derivative acts on sigma. So I might as well do this. And so what I have here, I have a total derivative. And so the integral down here, I can write down as the integral over the boundary. What I will have, I can use a theorem to relate an integral of total derivative. So I will have NA JA times A of sigma naught. And so this should be equal to 2 pi over I epsilon delta A of sigma naught.
Can I ask a question?
Yeah.
It might be stupid, but I'm just a bit confused. If you do the usual QFT, you calculate the word identity.
Yep.
And then if the current is exactly divergenceless, then the surface integral should give a 0, right? So
Well,
vanish, right?
right. So
But wait,
Well, that was before, well, what you're saying that there will be a conservation of, there will be a conservation of current, right? And that's a correct statement if we don't insert any operator, right? So if we don't have any operator inserted, so one of the word identities, the simplest one you're mentioning is that you can think that I'm just going to put A an identity operator. So if A is an identity operator, by definition, it doesn't transform. So delta A equals to 0. So you see that actually the integral is 0 in that case. And that's a consequence of the word identities that we derived before. The first word identities that we derived is that if we construct a conserved current, then it's divergence free. So I don't quite understand your statement. I'm saying that that identity follows from this one. If I make a statement that this is an identity operator.
Yeah, but even you insert an operator which is not an identity, an arbitrary operator. Suppose we are doing things in real coordinates.
Yeah.
And even that's not an identity operator, it should still vanish. Is it still a total derivative? Then the surface integral should vanish.
We are deriving that it's not, right? And it neither it does in a normal.
Because you have poles inside.
Well, I mean that's a formal way that we will see later. But the way to think of this is that we are preparing some state, right? So if you wish that relation was a relation, well, I mean. Yeah, well, I guess I cannot say.
It's okay.
Yeah. So it's so we're deriving a non-trivial word identities. Well, see, the thing is that we are assuming that the symmetry transformation acts on our operator as well in a non-trivial fashion. So probably what you used to think of is that some conserved quantity, and if it doesn't act on an operator, then you get exactly what you said. Because as long as the operator doesn't transform, if it's a scalar under symmetry transformation, then that thing is 0. So, okay. Anyway, maybe it will be it should be hopefully clearer as we move on. Okay, so the statement here is given in terms of coordinate sigma 1 and sigma 2. But something that we discussed is that we like our holomorphic and anti-holomorphic coordinates. And so what we can do, we can simply rewrite this relation in terms of z and z bar. And so this becomes an integral over a closed contour. So then I have jz dz minus jz bar dz bar with s a z naught z bar equals to 2 pi over epsilon a z naught. So in general, it's difficult to evaluate this integral exactly. And the thing that allows a simplification is when, so left-hand side simplifies, when jz is holomorphic, meaning that del bar of jz equals to 0, and correspondingly jz bar is anti-holomorphic, meaning that del of jz bar equals to 0. So in this case, we can use a residue theorem, right? So the residue theorem tells us that here it will be 2 pi I times a residue of jz a of z naught bar, right? And then you have a minus sign, but the residue theorem will come with additional conjugate of I. So I will have plus 2 pi I residue of jz bar A. Okay? And so it must be equal to 2 pi over epsilon delta A z naught. Okay? So let me just remind you what the residue is. So if I have a function f of z, then the residue of this function f of z is a coefficient in a Laurent expansion of this function, and we pick up the coefficient of 1 over z, right? So what I mean by that is that f of z equals some Laurent series fn z to the n plus 1, and so the residue f of z is going to be equal to f. Right? And so similarly, it's defined for an anti-holomorphic function. Okay. So again, let's don't lose track what we are trying to do. So what we developed so far, we used a path integral formulation of this two-dimensional field theory, and we are on our route to discover conformal symmetry, right? So we learned how various operators transform, and now we will play with some examples, right? So any questions before we move? Okay, so this is going to be our basic formula, actually this one. So let me write it down one last time. I'm just going to write it down in this form as residue z goes to z naught, jz, z naught bar, plus residue bar, z bar goes to z naught bar, jz bar, a z naught bar equals 1 over I epsilon bar. So this ordered identity is very powerful, so the point here is that we will end up eventually using the OPEs. We will use the OPEs to extract the 1 over z like dependence, 1 over z minus z naught dependence, and in this way we will learn how our operators transform. So once we understand what the conformal symmetry group is, we will find out that actually there is a very close relation between operator product expansions in the conformal field theory and the singular part of the transformation of operators. Yep. Yep.
Can you say Jelly holomorphic, Jelly bipartial holomorphic?
Yep.
To mean this J is conserved.
Right. So in these complex notations, that's the same statement as saying that J is conserved.
But it's come back to Eden's question. Whether J should be vanished.
No, it's not vanished. I've noticed there is no del J in this. For example, look at these formulas that we derived. There is no sure. If I add with del on J, I will get 0. I'm not saying this. But the eventual expressions that we derive, there is no del acting. Okay. And moreover, you know that classically, so again, all these relations, the thing that probably confuses is that all these relations should be understood as expectation values, right? So it's very similar, for example, when we were studying, just at the very beginning, the classical equations of motion. So for example, there was always classical equation of motion that del bar, del x was equal to 0. But then we found, when we looked carefully at the path integral, we found a piece which was delta function, right? The difference between the product of operators and the normal product of operators. And that piece was a quantum effect. Okay, so it is conceivable that these questions are related, are the same. You know, so and I think it's indeed the case. So classically, it will vanish, but there will be a quantum corrections, and the quantum corrections are actually responsible for this word identities. I want to emphasize that this is quantumly exact. Okay, so we didn't use any classical analysis, right? So we used the path integral formulation. All right, so very good. So let's move on and do a bunch of examples, and in particular, we want to test this a little bit scary looking formula in something that's very intuitive. And so let's do this. Well, so our basic theory, just free scalar fields on a wall chip, has a bunch of symmetries. And so one of the symmetries when delta x mu is shifted, right? So when we shift delta x mu by this amount, so our action is invariant. So what I want to do now is actually to construct a current, a conserved current, and as you absolutely correctly pointed out, pretty much the fact that it will be conserved will automatically guarantee that it decomposes into holomorphic and anti-holomorphic. So let's see this explicitly. So again, so we start with the action, which is 1 over 4 pi alpha prime d2 sigma del x squared, right? And so now, what we need to do in order to derive the current, we need to add a function rho of sigma, which has a compact support here. And so when we do that, so delta s will be 1 over 2 pi alpha prime. Okay. So absolute mu is a constant, so I'm just going to pull it out in front, and then I have an integral of d2 sigma. Right? So there is a factor of 2 because I can vary either the first delta x or the second one. So that's why it becomes 1/2 here. And then 1 over x stays. Okay? And the other x, okay, sorry, I have to put both things here. And the other becomes just the derivative x on this rho function. Okay? So we have this variation of the action. And now something I want to remind you is the way how we define, again, we have to, in order to get all the signs right, we have to stick with our conventions. And so our conventions, how do we define the conserved current? So let me remind you how we did it. Well, so we said that the path integral d phi prime e to the minus s of phi prime was going to d phi e to the minus s phi, and then we wrote it as 1 plus I epsilon over 2 pi integral d2 sigma JA blah a rho, right, plus high order correction. And so it's clear that this piece, so the metric, if there is no contribution from the metric of the path integral, then all this piece up here must be minus the variation of the action under the symmetry transformations. So this tells me that the variation of the action must be minus I absolute over 2 pi, an integral over d2 sigma, and then I have JA del A of rho. Okay? I have never wrote so badly as I'm doing it today in various angles. Okay, so good. Okay, so in other words, what we have this relation epsilon a mu over 2 pi alpha prime must be equal to minus I epsilon over 2 pi, and then I have GA. Okay? Yeah, so except that I forgot del A X and Q. Okay, so in other words, if I write down JA is as AU, JU, A, indices, then this JA mu equals to minus plus I over alpha prime del A over X. Okay, so take a look at the level there and see if you have any questions. Okay. So automatically this current comes up conserved. And so if I go to holomorphic and anti-holomorphic indices, so I will have del of x mu and dz bar of mu that equals a little bit here alpha prime bar x mu. So the first one, as we know from our analysis of the field X, del X is holomorphic and del bar X is anti-holomorphic. So this current is holomorphic, as we claim, and this guy is anti-holomorphic. Okay. So what I want to do now, I want to, once we constructed this current, I want to use one of the operators, some simple operators, so that we can all check this word identity and see that it makes sense. Okay. Good. So the operator that I'm going to use is going to be my operator A. It is the IJX, okay, and it's a normal product. So what I want to do, I want to, and this is the first time we will learn how we can use the techniques of OPEs to compute the residues. So what we will do, we need to compute the residue of the product of these two operators. So we are computing this quantity out here. And so the way to do this, remember that when we have a normal ordering, then there are no singularities, right? So our normal ordered operator satisfies the classical equation of motions. And so the singularities can come only when we do contractions. So in this case, we have to do cross contractions, right? So there will be, so the only piece when I act, so the point is I want to write this down as a product of the IKX, right, plus cross contractions. And it's only cross contractions that are singular in the limit that goes to Z0. So I'm assuming this guy depends on Z0. So those guys can be singular, as that approach to Z0. Okay, which means that it is only the cross contractions that will contribute to the residues. And so you can play this game and you will see that the more, so a rule, and again, it's like an empirical rule, but you can check it when you do exercises. But the rule is the most singular in 1 over z minus z naught term comes from most cross contractions. Okay, so this example is very simple because in this case, the only cross contraction we can do is a single one, and the reason is that remember in the cross contraction we act with del over del x on the first operator and del over del x on the second one. So in this case, so that's thing equals to I over alpha prime. Then I have del x acted e to the I kx, right? So there is only one x here, so I can act only with one cross contraction. And so I'm going to use this sign to indicate that I don't care about non-singular term, and I'm going to write down only singular pieces. Okay? Only singular pieces. So I have I over alpha prime coming from here. Now each cross contraction brings down minus 1/2 alpha prime log absolute value of z, right? Squared. And now, so there will be a derivative active, one derivative because there is a derivative active on x. So there will be a derivative acting here. The other del over del x acts on this exponential. And so what we will have an exponential left over. So there will be an ikx left over. And there will be, it will bring down I over, I have to put an index here, mu. So it will bring down IKV. Okay, so is that clear? Again, I'm computing this del over del x mu. So the first one gives just a derivative on the cross contraction, and the second one gives me ik mu. But then there is this eta mu nu, so it will turn into ik mu. So eventually, so this becomes. So del of the log will give 1 over z minus z naught. And then I have I and minus, so it will be plus. So I have 1 over 2 z minus z naught, right? And then I have k mu here, and I have the operator that I started with. Okay. Good. So now we are in a position to actually compute the variation of this operator, right? So I did it for the holomorphic current, but I can do it as well for an anti-holomorphic current. So del bar x mu e to the ikx. And so you can see that nothing will actually change except that I will have z bar minus z naught, and then e to the ikx. Okay? So I want to keep this so that we can see what's actually going on. Right, and so what we are finding, so if I evaluate now the left-hand side, right, so the left-hand side gives me, so I'm just picking up the residue, so it's going to be equal k mu divided by 2 from the first residue, plus k mu divided by 2 from the second residue, times my operator. Okay? Questions? All right, guys, this is the simplest example. So we should all understand it. Okay? Good. So this equals to k mu times the operator, and the right hand side tells us that it must be also equal to I, what did we say, 1 over I epsilon, 1 over I epsilon of delta A. Okay? So in other words, the variation of our operator, so this is from word identities, that we derived, the variation of the operator must be equal to I k mu epsilon times A. Okay? And you can see that that's exactly what you expect, right? So if I have an operator A equals e to the I kx, and so if what I'm doing, I'm shifting x mu, so the symmetry that I'm doing, x mu goes to x mu plus epsilon, right? So what will happen is that my operator goes to e to the I kx plus I k mu epsilon, right? And so you can see that the variation of the symmetry transformation is precisely what we extracted from the word identities. Yes.
The indices in that thing don't seem to match up because you have a mu on one side and not on the other.
Sorry, what mu?
For delta A equals I k mu epsilon times A. On the last platform.
This one?
Not on the last platform. Yeah. On the line below it.
Yeah, I'm assuming that I vary only a specific direction, right?
Okay.
So not with the general vector A mu. Remember that we derived the conservation current, which was contracted with this A mu. And if you wish, I'm now choosing A mu to be 1 along a single mu direction and 0 along the others. And that's the way how we develop this extra mu index. Okay. All right, so any questions? Okay, so very good. So let's move to a much more interesting example, which will also allow us to practice a little bit more the techniques of computing the transformation properties of operators. And so our next example, there were lots of talk. Where did it go? My next example is going to be a symmetry transformation associated with a Wolfsheim translation. So this is only example 2. And so in understanding this example, we will find out that actually our scalar field theory in 2 dimensions has tons of symmetry, much more than what we thought about. So for now, we'll look at the symmetry transformation when when any of the coordinates transform as follows, epsilon times b of a. So b of a in principle is a constant, well, it must be a constant vector for it to be a symmetry, right? B of a is a constant. And it's clear that our action is invariant on the symmetry transformation. So what we're going to do right now, we're going to construct a conserved current associated with this symmetry transformation. And then we will discover that actually there is much more symmetries in the problem than just this obvious one. And that will lead us to a conformal group. Okay? All right, guys. So let's move on. First of all, is it clear that that's a symmetry? Okay, because x is a scalar, and this doesn't change the measure of integration. So the first step we need to do, well, so it's a scale. So let me say that sigma a goes to sigma a prime, which is sigma a plus epsilon b of a. So I'm going to be very specific here. And so what we know is that under any symmetry transformation on a wall chip, so our fields x mu are scalars, which means that x prime of sigma prime is the same as x mu evaluated at sigma. Now, the way how we define, so the first step we need to do is we need to compute, well, it's something that we will check here. How does our operator transform under the symmetry transformation? Well, delta x mu of sigma, right? So by definition, the way how we define this delta A, how does it transform? So it's x mu prime of sigma minus x mu of sigma. Okay? Now, I don't know what x mu prime of sigma is, but I know I know, yeah. So what I can do, so I'm thinking what's the easiest way. So let's look here. Let's look at this relation here. So I have the x mu prime of sigma plus plus delta sigma, right? So I'm making some abbreviation, is the same as x mu of sigma, right? So which means that x mu prime of sigma equals x mu of sigma minus delta c, right?
Why that is not a mu prime?
No, I'm just saying the statement. So this guy is sigma prime. So I'm using this identity. X mu of sigma prime equals x mu of sigma. Now, I'm writing down explicitly what sigma prime is. It's sigma plus delta
Mu
sigma.
prime should equal to mu.
Sorry?
Mu prime should equal.
Yeah, but prime, I mean a transformed operator. I'm not meaning that the index is different. Right, so that's, I don't know, let's put a hat or something like that. It didn't mean to say that it's a different index. Okay? So this is a very crucial step. Okay? And so you can make, well, I mean, it's easy to get lost in science. Yeah. Okay, so anyway, so that tells me that this is the same as x mu of sigma minus minus epsilon dA, right, minus xa of sigma. And so you can see that we can do a Taylor series expansion and retain only the first term, so it's going to be equal to minus dA, minus epsilon dA del A of x mu. Okay? So when we will go ahead and recheck our word identities, so this is what we expect, right? So this is the way how our operator transforms. Delta x mu equals to z. Okay, so very good. So the next step we need to construct a conserved current associated with a symmetry transformation. Okay, so again, our action is as before, and so delta s, the transformation of the action, is delta 1 over 4 pi alpha prime, the integral d2 sigma, and then I have del a x mu, del a x mu, and so I want to apply the transformation here to that, and so this is going to be equal 1 over 2 pi alpha prime, and then I have d2 sigma, and then I have del a x mu, del a delta x mu. Okay. So now delta x mu, remember we have to write down now, is as minus epsilon dA, some function. Well, actually, let me not talk about the function. So, it's equivalent to say that I'm going to make epsilon coordinate dependent. So then it's just epsilon as a function of sigma VA, and then I have del A of x mu. Okay? So now you can see that there is this additional, we put a different index here. So there is an additional derivative. And so in general, this variation will have two terms, right? So the first one, when the derivative acts on epsilon of sigma, and the second term comes when we'll have derivative acted on del x. And so I'm just going to write down the answer. It's going to be -1 over 2 pi alpha prime. So here I have an integral of d2 sigma del A x mu del A epsilon BB del B x mu. Right? So what I did here, I acted with the A derivative. Well, see, I'm sorry guys, I keep switching indices, but you are very good, so you'll figure out the indices are constructed. So what I call A and B actually change the names because it's equality sign. But it's clear what happens. So this term comes when I act with a derivative on epsilon. And then there is another piece. So then there is another piece. So dB over 2 pi alpha prime. And then I have d2 sigma. And then I have del A of x mu, and then I have del B del A of x mu times epsilon. Okay? Right. So notice what happened is that in this case I act with the derivative. So this one actually has the same convention as up here. Just to confuse people. Yeah.
Right, and now we have local transformation. I mean, epsilon is sigma dependent.
Yeah.
So you should change the measure. I mean, d sigma is now.
We'll change it.
Can you get that copy and it's not working?
Right. So and.
Yes, but you always take the first one.
Yes, so that's what I wanted to say is that the square root, the transformation of the measure will be. I'm a little bit oscillating. I know that it comes up in real computation always that the variation of the measure is a second order in the variation of the coordinates, but so it must be the case. So let's take it and move on. I'm sure that it can be proved, but must be right. Especially it looks like the same thing. Okay, so very good. So now we have to massage this and put it in a form where we can read off what do we mean by our self-current. So let's go ahead. Okay. So remember we need to put it in the following form, right? So what is the variation? So in order to extract what's our current, the variation of minus the action must be of this form. I absolutely, well, given that I make epsilon rho u epsilon, so it's going to be I over 2 pi d2 sigma g. And then this is the current that we are after, and then del A of epsilon. Okay, so once we put the variation of the action in this form, whereas there is an integral with the worldsheet times a derivative of the parameter of infinitesimal transformation, whatever is left with this right convention is what we should declare to be our current. Okay, so let's go ahead and see what we have. So this piece is nice, but this piece is not. So this piece is in a wrong form. We don't have a derivative acted on epsilon. And so what we have to do first, we have to make sure that there is a derivative acting on epsilon, and then we can put it in this form. So let's look at the second piece. Okay. So the second piece has del A x mu, and then I have del B del A of x mu, right, times an epsilon. So what I can do, I can write this down as 1/2 del B, okay, del A x mu, del A x mu, okay. So I made a derivative del B acted on both axes, and there is a factor of 1/2 associated with that. And now I have epsilon. And so what I can do now, I can actually integrate by parts, drop the surface terms. And so this piece will transform into -1/2 del x squared times del B acted on x. Okay, so there will be a minus sign in front. So now both of the pieces are of the form as we needed. And so given that I'm moving much more slower than I want to, would you guys allow me now to just write down the answer? I went through all the complicated parts, or should I do slow steps and say what the answer for JA is? Yes or no? Okay. So the only subtlety here was this one. But the rest is really just combining the pieces and looking, extracting what J is. So if we do that, the answer will come up to be JA equals to BB over I alpha prime, and then I have del A x mu, del B x mu, minus 1/2 delta AB del x squared. Okay? So I constructed a conserved current, so much like in the previous case, when we had a space-time index, and we kind of added one additional index. So I'm just going to define, what will be familiar to us as a stress energy tensor. So this guy is minus 1 over alpha prime, and then I have del A x mu, del B x mu minus 1/2 delta AB delta x squared. Okay, so if I define a stress energy tensor in this way, again, this is just a definition. So my conserved current, I can write down in the form as minus 1 over I BB TAB, which is I BB TAB. Okay? Good. So what we did so far, right? We constructed a conserved current associated with translations on the wall shape. It's natural to expect that the conserved current will be related to the wall sheet stress energy tensor, and that's exactly what we found. Okay. One thing that I want to mention is that now I want to define the stress energy tensor as an operator, including full quantum corrections. And so there is an ambiguity. How do I define a stress energy tensor? And the ambiguity, for example, in the model that we talk about, is associated with whether or not I will take a normal ordering product. And so in particular, the normal ordering product can bring in some additional constants, and we'll talk about this ambiguities somewhat later. So what I'm going to do, I'm going to just declare what do I mean by stress energy tensor in my quantum field theory. Some of the examples that we must consider today, otherwise we will hopelessly fall behind, the way I want you to think about CFT and the way we will come to think about the CFT is that we'll define a set of basic operators, which I will introduce shortly, and then I will tell you what the stress energy tensor is. And so it's a property of the stress energy tensor and these basic operators, primary operators, that will define for us the CFT. So thinking in this manner, I can just declare in quantum, well, in the conformal field theory. So I'm just going to define the stress energy tensor precisely by the same relation, except that whatever ambiguity you thought, I will remove it by saying that it will be normal ordering. Okay, so it's normal ordering. So now we are in a position to discuss a new subject, a new topic, and the new topic will be conformal invariance. So notice that if I have this definition of the stress energy tensor, so the stress energy tensor is traceless, TAA is automatically vanishing. And so remember that the way how we lower and raise the indices, so in a complex variables, GZ bar equals to 2, and G Z bar Z also equals to 2, and those are the only non-vanishing components of the metric. So what this tells me, so the fact that the stress energy tensor is traceless, if I go to holomorphic and anti-holomorphic variables, this tells me that this guy, for example, vanishes. So this guy vanishes, and this guy vanishes. Okay. So in particular, the only components of the stress energy tensor that I have left are only non-vanishing components of TAB are TZZ and TZ bar, that bar. Okay, so those are the only components, so far we use just the condition that our stress energy tensor is traceless, but now we use conservation law, right? So use conservation of the current. Right, so strictly speaking, the way how we should write down the conservation of the current is that nabla A JA equals to 0, but this way better. But notice that our current defined on top of the stress energy tensor up to a constant function, V of B. And so this is equivalent to say that nabla A of T TAB equals to 0. So we have a conservation law for the full stress energy tensor. So now I'm going to write this down in holomorphic and anti-holomorphic coordinates. So what do I have? So I have the del bar of tz v plus del of t z bar v equals to 0. Okay. So what I did here, I have to lower this index, and once I lower this index, I know that the metric only links together holomorphic and anti-holomorphic coordinate. That's why it's del bar here, the index z, del here, index z bar, and the left-hand change the other index. Okay. So now I have two choices. Of course, I can choose B to be equal to z. Okay. So B, my holomorphic index, this piece goes away. Okay, because I have T Z bar Z, and it must vanish because the stress energy tensor is traceless. So when I choose my index B to be equal to Z, I'll find that del bar of T Z equals to 0. And if I choose my index B to be equal to Z bar, I will find del of T Z bar equals to 0. So what we discovered with you is that the invariance of the theory under this Walsh translation put the constraints on the stress energy tensor. And so in particular, it implies that T ZZ is actually a holomorphic function. So I'm going to drop an indices ZZ and write it down as a holomorphic function. And the other one is an anti-holomorphic. So and TZ bar is anti-holomorphic. I think I use it well here. Okay, very good. Good. So now we can go ahead and ask, we have this expression for the stress energy tensor written in arbitrary, well, written in a kind of sigma 1, sigma 2 frame. But how does it look like? How does it look like in holomorphic frame, right? And so you can just easily see what will happen. So for this T of Z, which is equal when both indices are holomorphic, only the first piece will survive, right? The second piece will not, because that second piece will be GZZ, which vanishes, right? Once I go into holomorphic frame. So T of Z is minus 1 over alpha prime, and then I have del x mu, del of x mu. And you can, again, explicitly see that it must be a holomorphic because del x's are holomorphic. And so similarly, I have T tilde of Z bar minus 1 over alpha prime, del x mu bar, del bar of x mu. Okay, so very good. So now, some things that I'm not going to do, okay? So a good exercise, but I'm going to do something more complicated in which this exercise will be a part of the general story. So a good exercise is to check, and you can actually, you don't have to go to holomorphic variables, you can go back to the normal AB form of the stress energy. A good way to exercise to check that what identities satisfied for delta sigma A equals minus epsilon of sigma E. Right? So when we make this a plus sign. So when we make these worldsheet translations, all the word identities will satisfy. And it's just, again, the way to do this is that you have to compute the residues, and the way you compute the residues by computing an LPE and pulling out the terms from the cross contractions. All right, so good. So any questions so far? So remember, let's go back to our current, right? So our current is given by A, EA, TAB, and so what we showed that this current is conserved, right? The conservation of this current implied this T was holomorphic and T tilde was anti-holomorphic. So, but in this form, when we derived this, V of A was a constant, right? So what we did, we made a shift, an arbitrary coordinate-dependent shift, but this vector V of A was a constant. But now what we can do, we can generalize conserved currents, right? So we can construct JZ. Do I call it JZ? No. So generalization. Generalization of the current here. And so the way I'm going to construct it, I'm going to declare my new current, which is I, P of Z, T of Z, and then JZ bar tilde is going to be equal to I, V of Z bar, T tilde of Z bar, right? So remember that conservation of the current, right? So this is something that you mentioned before. And it's simply a consequence of going from one frame to another. If we have conservation of the current written in this form, then this is the same as saying that del bar of Jz plus del J bar equals to 0. So those are just rewriting of the index contraction into frames. And so you can explicitly see that the new current that I constructed by hand, okay, I just declared I want to look at the symmetry property. It automatically conserved. So the new currents are conserved provided V of Z is holomorphic. So as long as my function V of Z is holomorphic, then the whole product is a holomorphic, and so it will vanish. Okay, so very good. So what we want to do now is that, well, what we did, we discovered a new conserved current, and we want to know. So the current is associated with some symmetries, and the question we ask, what are the symmetries corresponding to this transformation? And so the symmetries running just a little bit ahead will be the conformal transformations. But let's find out it specifically. So the point is, we want to find delta x, how we feel delta x transforms due to symmetries associated with these new currents, Jz and Jz bar.
Yep. Maybe just it's not the symmetry if we put VA there depending on Z. So it's.
That's why I said that up to there, it was constant.
It was
Then
constant.
I said, I'm just going to do this.
So, but
I don't know what the symmetries are, and that's what we are discovering by using word identities.
so
So in order to construct, to make sure it's a symmetry, I have to have a conserved current. And that's what exactly I did. I showed that there is a conserved current. I don't know yet what symmetry is. That's what we are finding.
so it's not. It will not that.
It will contain that, and it will be much, much larger. So the conformal symmetry of that we will discover is hidden. Okay, and if you wish, we're finding something that's hidden. Okay, so is the logic clear? All right. So remember that the exercise we have to do is to use word identities, right? So something that you love by now. So let me write it down once more time. This word identity. Do I have? it doesn't matter. I'm happy to write it one more time. So the word identity tells us that the residue of the current with any operator that goes to Z0 plus residue bar Z bar goes Z bar naught, J Z tilde A equals 1 over I epsilon delta A. Okay, so now you can see the fundamental role of this word identity, because what we did, we constructed a conserved current, but now it will allow us to figure out how does our operators transform, because all I have to do is to compute the OPEs, right? Well, compute the residues and so on. So our operator A is X mu, right? And so, so what we need to, the current, so Jz is IDP. And so what we need to do, we need to compute OPE of stress energy tensor with our field. So in other words, we have to compute this OPE. Okay. And again, we care only, well, for now I can write down the exact equality sign, because I'm going to write it down -1 over alpha phi del x as a function of that. And then I have x mu Z0 phi. Okay? So the only thing that we care is the most singular piece. But actually not the most singular piece. What we care about is the piece that will produce 1 over z minus z0 singularity. And that piece will come from a single contraction, as you can see. So if I have so this is the same as -1 over alpha times. So I'm claiming that it comes from a single contraction. So what this means that I have minus alpha prime over 2 log z minus z0 absolute value squared. So that's a factor that come from the contraction. But there is a symmetry factor, right? Because one of the derivatives can act on either of these fields, right? So the symmetry factor comes because it can act on any of them. So there is a factor of 2 from the symmetry. And then what will happen is that I have to act with del on this log, because when I do a variation, instead of varying x, I vary del x. So there is a z derivative coming here. So that's one piece of the cross contraction acts on the first operator. The other piece will act on the second operator, and it will produce nothing. But then I will have a leftover of del of x, and now I have to evaluate it as a node, right? Because again, I'm looking at the most singular piece, and difference between that and that not is just going to be will produce a non-singular piece. So is this clear so far? Okay, pretty good. So now let's go ahead and compute what do we have. So what we are finding that t x mu, so the singular piece is just when I act with this, d z minus z naught, and then I have del x of z naught. Okay. So you see that that's exactly the piece that will contribute in a non-trivial fashion to a residue. And so just to complete the analysis, there will be a similar piece coming from the anti-holomorphic part. And so this will be 1 over z bar and z bar home del bar. very good. So now we can use our water reactive, which is up there. So the residue is going to be simply that coefficient. And so what do we have? We have the del x of z naught plus del bar x of z naught bar. Okay. Okay. So this is just sparse energy tensor, but I have to take the residue of the current. So there is a factor IV here, right? And there is a factor IV bar here. Okay? And so this must be equal to 1 over I epsilon, and then I have delta x due to the symmetry transformation. So, so what we discovered with you that this very mysterious new current that we constructed produces a symmetry transformation that are of the following type. So delta x mu equals to minus epsilon v of z naught. Be careful, and this guy is z naught times del of x. And then I have minus epsilon v bar of z naught, and del bar of x. So that's a symmetry transformation. What is it? Okay, and so, well, it's easy to guess, right? So you already guessed, because the symmetry transformations that we are dealing with is z naught goes to z naught plus epsilon v of z naught, right? Well, let me drop the z naught index, right? So all of these guys depend on z naught. So I'm just going to erase z naught index here. So the symmetry transformation I'm talking about is this symmetry transformation. And the reason for that is simple. Because delta x mu is the same as x mu prime of z prime z bar prime minus x mu of z bar, which is x mu z minus epsilon v, z minus epsilon v bar minus x mu. Right? And so when you do your Taylor series expansion, this is exactly what you find out. It's minus epsilon v del x minus epsilon v bar del bar of x. So Alex was absolutely right. So the only symmetry that we saw before, when we shift coordinate on the wall sheet by a constant, actually that answers your question. Somebody asked me about the determinant. The answer is trivial because when we were deriving that before, our coordinate shift was a constant, right? So we made a shift. It is only when the shift is a constant, then it was a symmetry transformation. Naive, well, okay, the obvious symmetry. And when we did the analysis and compute the current, we need to make, as usual, the constant shift position dependent. That's what we did. So there are no subtleties whatsoever associated with determinants here. However, what we are finding now, we are finding that actually the theory enjoys much larger symmetry. And so instead of shifting coordinate by a constant, we discovered that there is a shift to leading order by an arbitrary function, and that's an infinitesimal transformation for z goes to z prime equals f of z. So in other words, our theory, free scalar field theory, enjoys this huge symmetry when we change a Wilczek coordinate by an arbitrary function. So how do we classify this symmetry, and what are the kind of basic building blocks of this group of transformations? So as I said, F is, so the only constraint, well, we have to continue here. So the only constraint is that F is a holomorphic function. So as long as it is holomorphic, then our discussion goes through. Okay. And so some of the basic, well, first of all, obviously, shift is part of the conformal group, right? So it's just f of z is z plus a constant. But then there are lots of other interesting transformations. So in particular, so shifts in rotation, they are obvious, right? But then there are an interesting one. So an interesting one comes when we take f of z equal to psi times z. So if the absolute value of this psi is 1, then it's just a rotation. So if absolute value equals 1, so just a rotation, but in general, it's rotation and rescaling. But in general, so it's rotation plus scaling. And so what we are finding is that our theory is secretly invariant on the scale transformations. Okay, so scale invariant. That's not exactly the conformal symmetry group. So in order to form the full conformal symmetry group, so first of all, okay, I guess I'm just going to say very few words here. So we are, our discussion is in 2 dimensions, but we can ask the question, what's the analog of the symmetry in higher dimensions, right? And indeed, in high dimensions, we can construct scale invariants as well. So we can construct scale invariant series, and we can construct the scaling symmetry. And what usually happens, though honestly I haven't seen the proof, is that whenever you have the scaling symmetry, there is an additional symmetry which is of the following type. So now, okay, how do I call coordinates in d dimensions? Call it y. X is we use for fields, right? So y prime goes to y prime squared equals to y mu over to y squared. So there is, in general, in d dimensions, it turns out that when your theory has a scaling symmetry, meaning that y mu goes to lambda times y mu, so there is this symmetry, then, though I don't know the proof, what always happens is that you, on top of that, you have this additional symmetry which is called special conformal transformation. And so in general, the conformal group in higher dimensions is generated by translations, rotation, scaling, and the special conformal symmetry transformation. So the 2 dimension is special. So in 2 dimensions, the conformal symmetry group is much, much larger. Because this, you might guess, is just one function, one specific function. And a conformal symmetry group in 2 dimensions is an arbitrary function, so it's much, much faster space. That's actually the reason why conformal theories in 2 dimensions are much easier. Because you have so much more symmetry, and so the symmetry puts more constraints on the theory, something that we're going to discover right now. Okay, so, yeah.
And your zeta or what? Cassine?
No, I'm saying that,
is it a constant, a global one or local?
So in this discussion, I'm talking about the global scaling, right? So, but of course, in the CFT, because f is arbitrary holomorphic function, you can have local rescaling different at each point.
But so far you assume that X mu is invariant under the.
No, what I was saying, okay, so I went into this discussion, which I probably shouldn't have, that I wanted to contrast the conformal symmetries in 2 dimensions and in higher dimensions, okay? And so, so in 2 dimensions, there is a huge, if you wish, group, right? So the generators are pretty much the set of any holomorphic function. Any holomorphic function is a member of conformal symmetry group. Now, in higher dimensions, I was telling that a conformal symmetry is generated by translations, rotations, global scalings, and what I call special conformal transformations. Those are like inversions on the circle. So that's a much smaller set of generators. And
I'm asking a different thing. I'm asking if that's a local transformation, then the X mu must be also shouldn't be invariant under the transformation such that it can compensate.
No. Again, so again, what we are talking about is we're talking about groups that acts on the worldsheet coordinates, right? So we decided to declare that our fields X mu are scalars after this transformation, right? So we explicitly said that they do not transform. And it is in this way we discover the conformal symmetry, right? So this line that I was writing here, when I was deriving how does my field transform, used explicitly the fact that X mu is a scalar. Okay? So naively, what you might think is that, look, what you're doing the almost arbitrary transformation of coordinates, and your theory is invariant. Why this is not like 2-dimensional gravity, okay? So, so it's not, and so it's not. Well, first of all, it's not an arbitrary, right? The transformations that we are allowed to do in conformal series are the one that I conformal scaling. And second, we have to remember that the series that we started is a series on a flat worldsheet. Okay, so the metric on the worldsheet was flat, so there is no graviton. Okay? So it's not, it's just still a quantum field theory, just a quantum field theory which has happened to have this huge amount of symmetry. All right, guys. So that's a general spiel. And now, let's go ahead and show that conformal invariance actually put a lot of constraint on OPEs of operators with stress energy. So specifically, so what we are discussing is conformal invariance and OPEs. And so in this discussion, we will discover our basic kind of operators of the CFD. So the claim is the following. So if I take a stress energy tensor, and I take any operator, I choose Z naught at 0. Joe Polchinski often does it. So this OPE, right? So I can write down in the following form. So I can extract the singular part of the OPEs. So I'm just going to write it down that n plus 1 am 0, 0, and then there are non-singular pieces. Okay. So in general, when I have an operator product extension, there will be some coefficients, right, times operators, and some of those coefficients will be singular, and some of them will be non-singular. So I pull out the singular piece of the OPE. And so the claim that I'm going to make and prove to you is that all these operators, all these singular pieces in the OPEs are completely completely determined by conformal transformation. Right? So in other words, if you tell me, so you have an operator, you tell me how does this operator transform on the conformal symmetry group of the theory, I will tell you exactly the coefficients of this operator for projection. I will tell you exactly what are these operators that come in a singular part.
Yeah. Why n just go from 0 to infinity? Why?
Because if n is negative, then that will be numerator, and those will be non-singular pieces.
Oh, wow.
Okay, so the other guys are up here. And you already noticed from the beginning of the discussion, it's only the singular pieces that carry interesting information. Okay, so so what we're going to do, we just going to use our word identity, right, to prove that statement. So we look at the current associated with conformal transformation given in this way. And so what we need to do, we need to compute the residue. So we suppose I'm looking now only at the holomorphic part of the transformations. So I'm just going to look at the residue z goes to 0, j of that, a of 0, 0 bar. And then this equals to 1 over I epsilon delta A under conformal transformations, right? So, so what this guy is, so let's evaluate it. So this is the residue that goes to 0. And then here I have IV d of that. And then I have t times a, right? What enters here is t of z, a of 0. But instead of writing it as a product of operators, I can use OPE, which is given there. So OPE will be sum n equals 0 to infinity, 1 over z n plus 1. And then I have a n 0, 0 bar plus non-singular piece. And so it's equal to 1 over I epsilon delta. Okay? So you can see that we used OPEs and word identities to relate this residue to the variation of our operator under conformal transformations. So now you explicitly see that because this guy is holomorphic, the non-singular pieces will not contribute to a residue. Right? So a residue of a holomorphic function is 0, right? It doesn't have any poles. And so we just need to see where the pole in this expression will come from. So remember that V is a holomorphic function, which means that I can write down there a nice Taylor series expansion. I'm just going to write down V of z with sum k equals 0 to infinity del k of V over k factorial, right? Z to the power k, right? So that's 0. So what I did is just a Taylor series expansion for the function. And you can see that the pole, the simple pole in this relation will come when I have del n acted on V over n factorial, right? So that brings z to the n. And so if I will have z to the n here, I will have a simple pole. So the residue will simply be del n of V over n factorial, because there is I in front here, and times a n of 0, 0 bar, right? Also at 0, And so this sum, so that's what comes from our residues, sum from 0 to infinity. So this guy equals to 1 over I epsilon delta A. Okay. So actually, I just computed a holomorphic piece, and then you can extract a non-holomorphic piece as well. Sorry, anti-holomorphic piece. Okay. So it's the sum of these two guys equals the transformation. So in other words, if you take an operator and transform it under conformal symmetry transformation, right? Then if I do an expansion in terms of this parameter B, right, remember our conformal symmetry transformation, that goes to that plus epsilon. B is a function of that. So if I do that, and then I write down this, this expression as a function of derivatives of the symmetry transformation, then I have these pieces A sub n. So what we did prove that there is a relation between transformation of operator and coefficients of the OPs with the stress energy tensors. So let me write down one last, well, actually I wrote it already, so I'm not going to do it. Good. So, so now let's use this knowledge and talk about some special operators. Okay. So what we're going to do, we're going to consider. So up to now, A was an arbitrary operator, and so now we introduce a basis of operators. Right. So consider a basis of operators, which are eigenvalues under the scale transformation, right? So this transformation with a constant psi, right? So a global rescaling, that's what I would call scale transformation. So consider a basis of operators which are eigenvalue, which are eigenstates. Eigenstates of rigid scale transformation. Okay. So what does that mean? This means that if I have an operator A, so Z1, under conformal transformation, it would go to some other operator, A prime, Z prime, Z prime bar. So by definition, we call this operator basis. Basic, if it transforms in this manner, minus H, psi bar, minus H tilde, AF Z bar. Okay. So this is a transformation on the rigid scale that goes to that side. So these numbers, H tilde, so those are numbers, and they are called conformal weights. Okay. So in particular, one of the operators of this type that we know is our field X, right? So what are conformal weights of X? 0, 0, right? It exactly transforms in this form with those guys are 0, 0. But in general, this is something that I don't want to spend time here. You can sort it out for yourself. So the sum of these two numbers is related to a dimension of operator. So this is a dimension of operator, dimension of A, and the difference is the spin. And by spin, I mean the charge under rotations on a plane. Okay. Good. So this is just a definition. This is a set of basic operators. So some properties, if we deal with this set of operators, so some properties are very simple. So if I act with del z on an operator, what will happen with my weights? Okay, so I have an operator with weights h tilde. So now when I act with del z on the operator, what I'm doing, I'm increasing this weight. Is it obvious? No? Let me write it down and then show you that it's obvious. So those are the weights of the new operator. So we started with the old operator, which was A. Okay? And so the old operator was transforming as whatever, minus h tilde A. Right? Now, the new operator is of this type, right? And so I'm asking how will this operator transform? Well, so this guy is del over del z, which will go into del over del z prime, which is the same as psi to the minus 1 del over del z. So you know that del z A operator will go to psi minus 1, psi minus h, psi minus h tilde, del A. Right? So when you act with del on your operator, you increase the holomorphic weight by 1 unit. Right? So this is holomorphic weight, this is m-vector. Okay, and similarly, so if I act with del bar, so what happens is, again, this is only true for operators which are in our basic sets, right? So those are the operators that have well-defined transformations. So this guy goes into h tilde plus 1. So what we want to do now, I promised you that the operator product expansion with the stress energy tensor is determined by the transformation property. So we choose our basic operators, and so now I have to be true to my promise. I have to show you that once I know this, I can determine some transformation properties, some coefficients in the OP, right? So let's see how it goes. So the only thing we know is that how our operator in the basic set transform under rigid scale transformation. So what we're going to do is consider infinitesimal rigid scale transformations. So in particular, we're going to assume that z prime, so z goes to z prime, which is z plus absolute times z, right? So absolute is a constant, and what I did a rescaling. So in other words, this psi parameter is 1 plus x. Okay? So if I look at this, right, so my function v of z, with which I'm doing my infinitesimal conformal transformation, is simply equal to z. Okay? Right, so in there, now if I want to classify this in the language of conformal transformation, I have to think of this as a transformation with an arbitrary v of z, and that tells me what's going on. So now I want to know how does my operator transform under infinitesimal transformation of this type. So I have a prime of z prime bar. So it's an operator of holomorphic weight h. And so all I'm doing here, I'm just transforming the holomorphic coordinate. So it will be 1 plus epsilon to the power of minus h. And then I have a of z bar. Okay? And so this equals to 1 minus epsilon times h and operator z bar. Okay, so very good. So the next step is actually compute the variation. The variation of my operator. So I have delta A. So by definition, the way how we always introduce it, so it's going to be equal to A prime z bar minus A z bar. Right? So this equals to. So I have to transform this, and then I have to shift a variable, right? Because in this transformation, so here I have to shift variable. So this becomes A of z minus epsilon z bar minus h epsilon A of z bar, and then I have to subtract A of z bar. So to leading order in epsilon, I will have minus epsilon times z times now A 0, and then I have minus epsilon times h. Okay. So remember that the general form of the formal transformation. So in general. So let me remind you again the formula. So if I have tz A of 0, 0 bar, so if we write down this, again, only singular pieces, n equals 0 to infinity, 1 over n plus 1, A of n of 0 comma 0. Okay, so then there is a correspondence between these an's, and so the correspondence is such that delta A to write down this formula again. So delta A equals minus epsilon sum n equals to 0 to infinity 1 over n factorial del n b A of n plus n the holomorphic. Okay. So what you can see is that we have a specific expression. How does my operators transform? And so what we found, I can rewrite it down in this form. So delta A takes the form minus epsilon times b delta A, right? Because remember that z equals to b. I want to restore back my function b. Well, actually, I'm going to write it down as A times A0, right? And then I have minus epsilon times del b, right? Times A1. So out of this infinite sum, I'm pulling out the first two terms, right? So in those terms are minus epsilon then A0 minus epsilon A1. So if you compare this line with this line, so what you are finding out is that this operator A0 equals to del A, right? And the operator A1 is going to be equal to H times A. So what we just did, we have a specific realization of this general idea. You give me the operator, you tell me how it transforms under conformal symmetry transformation. I'm going to tell you what the OPEs are. So what we do know now is that the OPE, so it must, so there is an infinite sum here, but one of the terms is one of the z squared A1 plus 1 over z A0 plus there are tons of other terms here. And so what we are finding is that when we deal with the basic operators, A1 is just H times A. So in this series of operator product expansion, this coefficient is H times A, and this guy is 1 over Z del A. Okay? And then there are other terms. Okay? So now you can see that if you happen to have an operator of a fixed conformal weight, right, the way to determine the weight of the operator is that you compute this OPE, and in fact you're guaranteed that you will get this 1 over z squared times h, where h is a weight. Of course, everything that I said can be extended to anti-holomorphic cases as well. You can ask me, okay, so this is all very good, but not so good, because what are these dots? Okay, how do we deal with these dots? And so in order to deal with these dots, you have to tell me how does my operator transform under more general conformal transformations. And so the transformation of the operator under more general conformal transformation will fix me these dots. So just staying with this rigid dilatations, I can do nothing. So what we're going to do after the break, 5 minutes, so we will discuss primary operators, the so-called primary operators, so primary fields or tensor operators. And so in particular, so let me just give a notation, and I'm just going to derive this after the break. So I will call operator O, curly O, to be my tensor field or primary operator. So if it transforms in the following way, so I have del z prime to the power minus h, and then I have del bar, z bar prime to the power minus h tilde times my old operator, O of the z bar. Okay, so this is a more general, a much narrow class of operators. So, so these operators in particular transform like basic operators under scale transformations, but they actually transform in a very specific manner, if you wish, covariantly under general holomorphic and anti-holomorphic changes of coordinates. And so what we will show is that these fields are called primary. They're very special. They're very special because what we will derive is that OPE has the following form. Well, first of all, it must be a basic operator, right? So it must have the same pieces as we derived before. So it must have keys of this type. Yeah. Oh, but the good thing is that nothing. So there is nothing else. So as far as singular piece is concerned, those primary fields or tensor operators have singularities, 1 over z squared and 1 over z. And moreover, the most singular piece clearly specify the conformal weights of my operator, plus non-singular. Okay, and so I'm going to derive this for you after the break. Okay, guys, 5 minutes. Any questions? You guys all right? Good.